Okay. So, on with galaxies in general. Okay, so, yeah, this actually finally, the Milky Way galaxy, we really can't take a picture of the Milky Way galaxy other than the disk, but we can see other galaxies. And so this is one of my favorite concepts. Can you see the Big Dipper here? Okay, so here's the bowl, and here's the handle of the Big Dipper. Okay, and so one of the early things that the Hubble Space Telescope did was to pick a point in the sky where there's nothing. Okay, and so this little area expanded, it looks like this. Okay, and that little area expanded, looks like that. Like, dang. And you can kind of see some shape to the, these are galaxies. These are like hundreds of millions of stars. Little disks, little, what we call little islands of disks. That's what galaxies kind of are. So ultimately, in this, we're going to come up with one of the many ways we age. We can determine how old our universe is. Actually has to do with studying galaxies. In general, if somebody uses the term cosmology, they're kind of talking about kind of the overall universe, kind of how it came to be as it is. We're talking more about cosmology after your test on next Thursday. So the three main types of galaxies, I'm going to highlight them in this field of galaxies. Okay, that type of that galaxy is called a spiral galaxy. That's one of the three main types. And then we have elliptical galaxies. Okay, irregular galaxies, they're not one of the three main types. They're kind of an in-between, or irregular galaxies, really baby galaxies look like this. They kind of are misshapen. The third type of galaxy you're going to see is a barred spiral galaxy. So you saw spirals, ellipticals, and barred spirals would be the third type. So this looks like actually it's like deja vu. This could have been what we looked at when we looked at considered the Milky Way galaxy. Okay, spiral arms, halo region, disk region, those clusters of stars we call globular clusters kind of in the halo region. So this is the Sombrero galaxy, and I think we saw this in one of the videos we watched part of. So when we talk about the spheroidal region around a galaxy, and we ran into this when we talked about the Milky Way, we're talking about kind of the halo region, okay? And like we talked about with the Milky Way, in the halo region of other galaxies too are the older stars. In the disk component, we have stars, young stars, old stars, kind of an assortment. Very pretty. So the third type of galaxy would be a barred spiral galaxy. And this is a really good example. You can see the bar of stars. So this would be the bulge. I need to change my color, don't I? And obviously you can see a major spiral arm coming out of the bar. Okay, right here. Very pretty. This kind of looks like an elliptical galaxy, but it's what's called a lenticular galaxy. Again, when I ask you on your test, wink, wink, what are the three main types of galaxies? This isn't a main one. We think this is maybe kind of an in-betweener between the spiral and elliptical. Very pretty, though. So these are photos. So spirals, barred spirals, and elliptical galaxies. Now, elliptical galaxies, as far as I can tell, and this actually says, they don't have any disk component to them. They're kind of like more ballish than frisbee-ish, okay? And we think that elliptical galaxies contain older stars. Elliptical galaxies can be packed full of stars, just crazily packed. Elliptical galaxy. If you were in the southern hemisphere, one of the things you might be able to see at night is I think this is called the Large Magellanic Cloud, or the LMC. But it's an example of a galaxy that's an irregular galaxy. All right. So Hubble came up with this thing called a tuning fork diagram. And so the tuning fork is like the old-fashioned where you had it has a handle and it has two prongs. Okay, and so you hit it on something, it goes, it gives you a certain note, okay? Tuning fork. So see if you can see the tuning fork here in Hubble's diagram. So E stands for elliptical galaxies. S stands for spiral galaxies. And SB stands for barred spiral galaxies.
And that's the three main ones.
And that's the three main ones, exactly.
I thought irregular galaxy was one of the three.
Nope.
Okay.
It's kind of an in-betweener. So are lenticulars.
Okay.
So elliptical, spirals, and barred spirals. I suppose it's very possible. I mean, that's just how I learned it. I suppose it's very possible that an astrophysicist has a different opinion.
Okay.
I'll go with him or her. Okay, but for the test, the three ones I'm looking for are the ones here on the tuning fork diagram. So one of the things we're going to talk about really soon is how the, can you guys see the nuclear, I'm going to put an X near the nuclear bulges. An X, okay. Where those X's are, that is the nuclear bulge. That's the center. And it kind of raises out a little bit from the disk. But some of them are kind of flat, some of them are big. Here's the deal. The more tightly wound the arms are, this one over here, this one right here, it almost looks like I can't see any spiral arms. That's because the arms are very tightly wound. And actually, you know, we had a review session like before class, and this is on the test. So tightly wound arms, and actually down here for these this barred spiral, their arms are tightly wound. And I don't know if you can tell or not, but it has a thick nuclear bulge. Thick bulge. I'll just put bulge. Okay.
So if they're tightly wound, they always have a good bulge.
Yeah, exactly. Exactly. And then the other extreme, you know, they have basically, these are loosely wound arms, you know, both the spirals and the barred spirals, and they have a relatively thin bulge. Exactly. And I can almost see that. It's a thin bulge, thick bulge. Oh, see, it was on like the next slide. So over here we have the larger bulge and the more tightly wound arms. That's what that's saying. But can you also see that we go ahead and this didn't make it to my test, but we actually, for the S or the SB, S being spiral and SB being barred spiral, we go ahead and put a little A, little B, little C to kind of subclassify them, how tightly wound their arms are. So, clear back in Unit 1, we kind of talked about how galaxies are organized, and we'll be talking more about that in Unit 5. But galaxies are clustered together, and then actually they're super clustered together. So they are organized. I guess I'll talk about it here. So the first, no, I don't. I was like, you're fine, you're fine. So the first kind of level of organization actually is called a galaxy cluster. And we are in the local group cluster. And so that's a cluster of galaxies. Almost see some, and we'll talk about this in Unit 5 too, but can you see the little wispies, like, does it, I'll try to kind of do this. Can you kind of see the little ring, okay, of something kind of, it's almost like a hidden picture. And that's actually called gravitational lensing of things beyond that. So, okay. So here's the deal. And I like this little animation. Just because two objects have the same brightness to us, you know, what we call apparent brightness, doesn't necessarily tell the whole story with regard to how much energy or the luminosity they're really pumping out. And just because they have the same brightness doesn't really say with regard to how close those objects are to us. So I thought this is pretty clever. Did we already do this one? Okay. So two objects with the same apparent brightness, the same brightness to us. So of course, you know what's going to happen when I reveal those two. They're two very different objects. They're two very different objects with regard to distance from us. We know which one's farther away. The lighthouse is farther away. Why is it farther away? This is what we do with stars. It's farther away because how is its brightness compared to the candle?
Same.
Yeah, it appears the same, but which one has more luminosity? Which one's pumping out? Yeah, exactly. The lighthouse is pumping out a lot more light. Okay, so this is a greater luminosity. Okay, but similar brightness. Okay, so it has similar brightness because it's so far away. Therefore, must be far away. In a minute, we have something called, it's a relationship that you've seen before. It basically says how far away an object is, its distance, is equal to how bright it is. Sorry, not how bright it is, its luminosity. Petered out on me. Oh, that's why it petered out on me. It's the luminosity, well, you can, divided by basically the square root of its brightness. Okay. So anyway, back to the slides. So what we're getting to now is we love the pictures that Hubble took. They're awesome. But one of the things we need to know to understand the nature of things is how far away those galaxies are. And actually there are, I want to say 6. Each time you see the word step, this is step 1, up to step 6, basically are looking at an object even farther away. So this is the closest objects. So one of the things we can do with objects that are relatively close is basically what radar does. What radar does, and I think we have a picture of a boat in a minute, but basically send a signal and look for the reflectivity of that signal. So this is radar. And obviously, the longer it takes for the signal to come back, the greater the distance between when it emitted and when it's bouncing off of. So actually, we could, on the scale of things in our solar system, do that too. So isn't that cute? That's a humongous radar going to send out a signal to these planets. So down there at the bottom, it says, how long does it take for the signal to come back? And here it says, then how much, what is the distance between us and that object? And we don't need to show the math. But isn't this adorable? What you do is you just take it. And I have pointed at what planet is that? What do you think? The second one? It's Venus, yeah. Very good, it's Venus. So it doesn't take very long to come back, and so it must be means it's pretty close. So let's just go ahead and go for, what planet is that one?
Mars.
Mars, very good. It took longer to come back, okay, and so it's farther away. That's kind of how that works. Okay, so that was the closest one. We talked about this way to gauge distance too. So this is a little bit farther away, and this is using parallax. Remember, we said that if an object is relatively close to you, we can gauge the distance of that object as we reposition ourselves. And in the case of a star, it's the 6 months apart, the Earth orbiting the sun, and that star moves against the background stars. And we can look at the what we call the parallax angle or the movement and get the distance. Okay, so that's step 2, a little bit farther than radar. Building up for several steps after this. This is building up to actually step 3 and a few. So this actually, does the slide look familiar? Basically, if you have an object that's oozing energy, like this object in the center of these 3 spheres, it's oozing in all directions, and the farther you are from that object, the light's going to get diluted, basically. And what it's saying is, it's kind of neat. For every one step, if your step is an AU, 1 astronomical unit, for every 1 step, it gets diluted by the distance squared. Okay, and it's kind of just showing you the dilution of light. So this actually is what I used a minute ago, and you guys put this on your test, your sheet, when we talked about the characteristics of stars. Remember, brightness is what we see it as, and luminosity is the energy it's pumping out. Okay, so we see it dimmer and dimmer as you increase distance. Okay, so here then is kind of what I tried to draw on a slide a minute ago. Okay, so we can get to distance. Okay, so so we're all on the same page here. We can get to distance if we know the energy it's pumping out. Okay, and we measure the brightness. Measure from Earth. So far, so good. So I'm going to introduce something called standard candles. And standard candles are indeed objects for which we know the energy it's pumping out. Okay. Standard, I'm going to say use standard candles. Standard candles. It's kind of like, it's very similar to going to your cupboard and you got your choices of your 40 watt, your 60 watt, I don't know, 25 watt. If you've got a dim place, you're going to light. But you know on the box how much energy it's pumping out. Okay. Yeah. So a standard candle is an object whose luminosity, how much energy it's pumping out, is known. So then all we got to do is, if we know an object, and these objects are going to come in the combination, the first object we're going to look at are main sequence stars. We kind of know how the luminosity of main sequence stars from an HR diagram. Okay, since we know that, we can compare it with how bright they are. Okay, and the way I think of it is how dimmed down they are, not dumbed down, but how dimmed down they are is an indication of, really mathematically, we can get to the distance of that object. Okay, so actually there are several steps that we can gauge how far away an object is based upon different standard candles. Okay, so this standard candle is, I don't know if you recognize your HR diagram up there, okay, because HR diagrams are surface temperature, hot, getting cooler, and we have the relative, actually what's different here though is the apparent brightness, not the luminosity. So it is a little different than your typical HR diagram. Okay. So it is different. So it's apparent brightness instead of how much it really is. So what that means is these should be, just put MS. If I put MS, okay, that's main sequence. That should be kind of the main sequence diagonal. So, do you guys buy this, that since the Hyades, which is a cluster of stars, and the Pleiades are cluster of stars, since they are brighter, apparently brighter, they have to be closer. Okay. The Pleiades are apparently dimmer, so they must be farther away. You recognize that main sequence. We know a lot about main sequence stars. Most stars are main sequence stars. So the Pleiades that you saw as the more distant stars, this is the Pleiades. And sometimes students will say that they enjoyed looking at the Little Dipper. Little Dipper. By the way, I was this close to getting binoculars for tonight, but it's kind of cloudy and it's kind of cold. So we'll see what next week brings, because I think that would be fun. Because we've got a big old box of them. But sometimes this is called the Seven Sisters. And it actually is in the constellation Taurus. Taurus the ball. So the reason they call it the Little Dipper, I think, is we kind of see a handle here and we kind of see a bucket there. But it's this big compared to the Little Dipper. It isn't this distinct, but the Big Dipper is like very big. Okay, so that was step 3. I'm kind of losing track of using a standard candle. Here's the next step, using a different standard candle. And actually, if you want to put step 4, this is kind of leading into step 4. What was our last one, step 3?
Yeah.
Good. This is leading into step 4, different standard candle. Do you remember we talked about main sequence stars? When they leave the main sequence, they kind of go into the whole giant region, but I said there's some wiggle there. Okay. There's different types of variable stars. There's the R.R. Lyre variable star, and there's the Cepheid variable star. And that's kind of in what we call the instability strip, wiggling. But it's a special star in that it wiggles. Its brightness varies with very periodic. Periodic. So what these wiggles, these little cycles, what you're seeing actually is the changes in the brightness of a Cepheid variable star. See, here's the catch. There are Cepheid variable stars that have different masses, and depending upon their mass, they will have different cycles or different periods. Okay. Yeah. So it kind of oozes with regard to being intense or not intense. Okay. So basically what this says is if you go ahead and track how quickly or how slowly it's doing this, you can use it as a standard candle by tracking how long it takes to complete one cycle. Okay, so the example here is if you have a star that Cepheid variable that takes 30 days to complete one cycle, okay, it corresponds to a standard candle of a luminosity just above 10,000 times the luminosity of our sun. That's the energy it's pumping out. Okay, so here's something that, and this is kind of cool, I'll go ahead and warn you, because this is the next step. This is actually something that Hubble saw a Cepheid variable in the Andromeda Galaxy. You're like, dude, how could you see that? I don't know. I looked through the telescope, at the Andromeda Galaxy. I'm like, I could not pick out a star to, okay? But that is just amazing. So you look at how it's cycling, and then it corresponds to a particular. Then you say, well, you went to your cabinet, and the light bulb you pulled out was 10,000 times the luminosity of. So like I said, that is step 4. And it's just using a different standard candle other than main sequence stars. I'm not going to play this little applet because it looks too complicated. Okay. Okay, so we look at and then we know the luminosity, and then we can compare its luminosity with its brightness and get distance again. So this is going to be actually step 5, I believe. Because the problem with Cepheid variable stars, I mentioned Andromeda Galaxy, Cepheid variable star, they're not as bright as a nova, okay? Supernova, sorry. So supernova events, the supernova what, type 1a, because that's what this is, actually have a known brightness. You can hang your hat on them. So this is a type 1a. So these actually are, you look top to bottom. So top is before the supernova. And see, to me, I'm like, I can't tell. That's so pixelated. And we get spoiled with the images we see. Okay, but that's a galaxy, far, far away. And this is an explosion occurring in that galaxy. Same with the next 2 pair. No supernova, supernova. I can almost see that one better. No supernova, supernova. Now, in defense of these pixelated pictures, it could be that galaxy, they look kind of irregular, don't they? The baby pictures of galaxies that we see are kind of blobby, irregular like that. Galaxies that only a mother could love. But we can see very far away, farther away than we could Cepheid variables, just because we know that they have a standard brightness. So back to the Cepheid variables a little bit. I think my things might be out of order. Maybe, maybe not. So actually, this is another term or another concept that's on your unit exam next week. I keep talking about it wasn't until 1920s that we understood the idea of a galaxy, and that's where this is coming up. So basically, before we understood the concept of a galaxy, they were seeing these fuzzy little patches up there, okay? Like I could bring in the poster of the Messier objects, and he saw these fuzzy little patches. He's like, I don't know what they are, but they're Messier objects. So there was this debate about those fuzzy patches, which we now know as galaxies. They're like, okay, so is that a nebula or is that a galaxy? Is that just an idea of a distant stars, a little island of its own, okay, or a galaxy? So then Edwin Hubble came in and used the Cepheid variable and gauged the distance to this beautiful object, which at the time didn't know whether it was a nebula or a galaxy. Now we know it's a galaxy. Andromeda Nebula just sounds funny. So there's Edwin Hubble at the business end of his telescope. Okay, and like I said, he studied a Cepheid variable, and he has much more patience than I do. But, is it Henrietta Leavitt? I'm not sure. But the person who came up with the concept of a Cepheid variable, going back to looking at its cycle to go back to its luminosity, that was a woman. So he used that. Okay, so then finally that debate was put to rest. I don't think in my notes I really answer how do we know how many galaxies they are, but it's kind of an issue of density. Remember, we started out with Hubble telescope, kind of looked in a region of the sky, there wasn't anything, and kind of came up with this many galaxies over there. So if you kind of extrapolate that further, we kind of come with how many galaxies there are. Okay. So one of the things we talked about clear back in Unit 1 is the fact that our universe is expanding. And actually in Unit 5, we're going to talk about how it's not just the fabric of space and time is getting bigger, okay? And not only is it expanding, but it's expanding faster and faster, which of course if something goes faster and faster, we say it's accelerating. So the expansion is accelerating. But one of the other things we've talked about is the Doppler effect. If something's coming towards you and it's sending a signal, it's blue shifted. That signal is blue shifted. Those waves are blue shifted. If something's going away from you and sending out a signal, then those waves are going to be elongated, redshift. So if the universe is expanding, okay, one of the things that we see actually is these galaxies, and I think we talked about this earlier, is these galaxies are all moving away from us. Okay, it's funny because are they all? No, they aren't all, most of them. We actually are on a collision course, as you know, with the Andromeda galaxy. But most galaxies, most galaxies are all moving away from us. The farther away the galaxy is from us, we're going to see here in a minute, the faster it's moving. But here's the redshift then. Remember how this works. Is this actually, you have to look back. Yeah, I think I looked at those wrong. The library sample is the top one. Okay, so the stationary sample, this is the lab sample or library sample. Okay, and this actually is showing you, for instance, instead of this little peak being right there, this little peak is right here. Okay, at longer wavelength, redshift. So, I guess I was reading through these slides getting ready for tonight, and like, so it's shifted 5% if you know what you're kind of quantifying things, and that actually means that it's going 5% the speed of light, which I guess I didn't realize. I know. So the more shifted the information is coming from a galaxy, then the faster it's going. So I'm going to show you this animation. It is totally adorable. And it kind of gets to the fact that if we're looking at an assortment of galaxies, like Hubble did, there's his assortment of galaxies. I can click on any of them. I'll click on that one. Okay. There's a little picture of it. It's Messier Object 106. Down here is important information. It says that galaxy is moving 448 kilometers per second from us, because we can use redshift to know how fast it's going from us. Okay. And I'm going to show you how we get to this, or maybe not. But the distance between us and the Milky Way galaxy and that galaxy is so many parsecs. Oh, okay, let's pick a different one. Guess it didn't like that because it went ahead and put the dot on there. So let's pick another dot. Let's pick, this one kind of looks like an elliptical galaxy up there. So it's Messier Object 87. So we're putting another dot here. Notice that it's moving a whopping 1,282 kilometers per second. That's how fast it's moving away from us. We can tell that by its redshift. And it actually is a distance of 18.4. M stands for mega. PC are parsecs. Remember, a parsec is like 1 parsec is 3 1/4 light years. Okay. Et cetera, et cetera. So You know, to come up with the HR diagrams that, that Hertzsprung and Russell did, they prepared what's called a scatter plot. And does that look like a scatter plot? It does, and that's what that is. Basically, what's plotted is how far away that galaxy is from our galaxy, or from us, from Earth, okay, along the x-axis. And along the y-axis is how fast is it going away from us. Okay, so basically what this is, and I'll go ahead and write it on here, is called, I want to say, it's Hubble's law, basically. Hubble's law. And so you can see what you plotted. Distance of the galaxy is from us and how fast away it's moving. Okay, so basically the farther it is from us, the faster it's moving, the greater the redshift. Oops. So those little black dots now you're seeing here are galaxies. Okay, and like you saw a minute ago, along the x-axis is how far away those galaxies are from us in millions of light years, and along the y-axis is how fast that galaxy is moving from us. So the farther away it is, how fast it's moving from us, yeah. The farther away it is from us, the faster its recessional motion. So this H0 actually is called Hubble's constant. It's all about Hubble, isn't it? You think the Hubble Space Telescope was named after this guy? Probably. So if you're familiar with an XY plot like this, actually, if you can draw a line like that, you can come up with what we call an equation for that line. And for every y, it's equal to the slope of that line times whatever x value is. Okay, so m is slope. And honestly, the slope is Hubble's constant. Now, I know that's a lot of math, but if you're kind of doing math anyway, we might as well bring it in, the equation of a line. Anybody know what B is? What is it?
The apparent brightness.
It could be the apparent brightness in astronomy. That makes sense. In math like this, actually, it's the where the line crosses the y-axis. It's called the y-intercept. So in this case, it's just it doesn't do much. Y-intercept. It's got the whole math thing going for it. So bottom line, though, aside from all that math stuff down there, actually, if you know the distance, you have a value for h0. You can calculate the velocity. And if you know the velocity, using h0, you can calculate the distance, because h0 is a constant. Okay, so there's our 5% redshift again. Something's moving away at 5% the speed of light, and lines are lengthened. So you gauge from the redshift, you can get to how fast it's going. Okay, and from how fast it's going, you can get to distance. Because you know h0. So let's see, what are we up to? Is this 6?
No.
Okay, step 6. We can use the redshift to get to the distance of a galaxy. So to, what we call rearrange or whatever, the relationship on the previous slide, solving for distance, and you divide both sides by h0, which is a constant, Hubble's constant, And here's how you calculate distance from the velocity. It's a division. So step 6. So it's funny how my step 6, like it was kind of the slides leading up to that, wasn't it? Okay. So the greater the redshift, the greater the redshift, the farther it is away, and actually we can use its recessional, what we call its recessional velocity, to get to distance. So this kind of summarizes all the stuff we've talked about so far. We talked about radar, and there's some overlap, definitely some overlap. We talked about parallax. Then we talked about using a standard candle, main sequence stars in a cluster, using Cepheid variables as a standard candle. But they kind of get dim after a while. We said that actually, where it says distance standards, the example we used was a supernova type 1A. We can see it even farther. We can use it as a standard candle. And then kind of overlaid on that, we can use Hubble's law. So this is a good place for a break, I think. Because we're just zooming along, aren't we? Yeah.
Will we only get through this tonight, or are we going to go into Unit 5?
I love, we're not going to do anything with Unit 5.
Okay.
So how many slides do we have left? Quite a few.